Berg, and I'm a PhD student at the University of Westminster. I'm one of the previous best student research presenters. Today it's my honour to facilitate the 5th in the series of seminars featuring the best student research from EI 2020 and to welcome you all here. I'd like to start by taking a moment to thank the individual donor who wishes to remain anonymous and the Royal Photographic Society for the support of this programme. Their support will help us provide EI registration grants and ensure the continuation of this online seminar series. I'd also like to thank Dolby and Sensors for this support of the 2020 Armand Dimont Best Paper Award. Before we begin, I'd like to take a few minutes to tell you about IS&T and the Electronic Imaging Symposium in particular. For those who are not familiar with IS&T, the Society is unique in that it brings together nearly equal parts number of international researchers and practitioners from the industry and academia. This makes it a great place for students such as myself to showcase work to prospective employers, and for those in the industry to learn more about exciting developments in the imaging research. IS&T spans imaging across applications from vision and capture through processing to the output. This conference, courses and journals offer a place to share the latest innovations with a network of others who have a love for and curiosity about the world of imaging. IS&T's breadth is best found in the Electronic Imaging Symposium, where 20 conferences and 25 courses offer everything from AR, VR, autonomous vehicles, big data, remote imaging, and mobile devices. Two great features about the EI are the open access proceedings and the ability to submit journal papers, which gives you a journal citation in lieu to the proceedings paper. And it also allows you to give a talk of your research. EI 2021 is now going to be held online. The EI conference committees are constructing programs that offer high quality papers with many opportunities to connect, communicate, and network as you would in person. EI can be a bit overwhelming at times, but it's a great place to learn about is the fundamental science and technology explored in academic settings can be incorporated into and improve our world. For students, it offers registration grants, a student YP research showcase, a demonstration session, which is a bit like show and tell, conference best paper awards, and the ability to take free courses. So I encourage you all to explore what EI has to offer and submit relevant research to it. So on to today's session. Our goal of the seminars is to engage you all into discussion after the talk. So we want everyone to feel free to take part in the conversation. To facilitate this, please take a minute to rename yourself in the Zoom to your first name, last name, plus your affiliation. This will help us to get to know each other better. We would also like to ask if you can turn on your webcam once the talk is finished during the discussion, so we can have more of a face-to-face discussion. Now gives me great pleasure to introduce Yasuyuki Fujihara, a doctoral student at Tohoku University, Japan. Yasuyuki is engaged in research on CMOS imaging sensors, especially for spectral imaging. In his spare time, he enjoys building IoT gadgets, and in today's session, he will be discussing a CMOS imaging sensor that is highly adaptive to applications where the automotive, medical, factory, automation fields due to its strong contrast of light illumination. So hope you all enjoy, and I'll pass you over to Yasuyuki. Thank you.
Okay. Thank you, Oliver. I'm Yasuyuki Fujihara from Tohoku University, Japan. Today, I'd like to talk about an over 120 dB dynamic range linear response single exposure CMOS image sensor with two-stage lateral overflow integration trench capacitors. This is outline of my presentation. First, I'll introduce the background. Second, I'd like to explain the CMOS image sensor, CIS, with two-stage lateral overflow integration trench capacitor. Then, I'll show the chip measurement results. Finally, I'll conclude my presentation. These days, sensing applications with CMOS image sensor, CIS, will play significant roles in healthcare, agriculture, environmental, automobile fields, and so on. For example, blood glucose sensor, sugar content meter, gas detector, and range sensor are more and more required for the safe and sustainable society in the IoT era. CIS, capturing target with strong light contrast, is more and more required, such as machine vision, automobile, analytical instruments, absorption imaging, and so on. To capture image with strong light contrast, over 120 dB wide dynamic range beyond human eyes is highly required. In addition, high SNR at switching point, linear response, single exposure are also important factors. In this slide, I'll explain the basic operation of the 4-transistor active pixel CIS. The cross-sectional view of the pixel is shown on the left. There is a photodiode, PD, a transfer transistor, T, and a reset switch, R. Between the T transistor and reset switch, there is a parasitic capacitance called floating diffusion, FD. Generated signal electrons are converted to voltage at FD. The voltage generated per electron is called conversion gain. If the conversion gain is high, it's better for high sensitivity signal reading. On the other hand, in order to increase the maximum number of signal electrons called full capacity, low conversion gain is better. So, CIS has a trade-off between sensitivity and saturation. To achieve wide dynamic range performance, low noise, and high fuel capacity, CIS have been studied. We aim for both low noise and high fuel capacity. In this sensor, we mainly focus on increasing fuel capacity. Several wide dynamic range technologies have been reported, such as logarithmic compression, multi-exposure, combination of photodiodes, and dual conversion gain, and LOFIC for increased effective saturation. In this work, we aim for wide dynamic range by increasing fuel capacity with LOFIC. The logarithmic compression approach utilizes the logarithmically compressed photocurrent output by using the substrate characteristics of MOSFET in highlight condition. The multiple exposure approach captures image with multiple exposure time. The approach with combination of photodiodes captures an image with multiple photodiodes with different size or light sensitivity in a single exposure. The dual conversion gain approach changes conversion gain by controlling a switch connected to a capacitor and floating diffusion in a pixel during horizontal blanking period. These approaches increase fuel capacity by decreasing sensitivity. The left figure shows the schematic of the LOFIC pixel. A LOFIC and a switch are added to a normal phototransistor pixel. The right figure shows the potential diagram. Under low illumination, the photoelectrons are converted at a small FD capacitance for high sensitivity. Under high illumination, overflow photoelectrons are accumulated in LOFIC and converted at FD plus LOFIC for high saturation. This approach allows independent design of conversion gain and fuel capacity. LOFIC achieves wide dynamic range with single photodiode and high linearity under single exposure. In the single-stage LOFIC, about 100 dB dynamic range and over 32 dB SNR at switching point was reported. When trying to increase the saturation side, sufficient SNR cannot be obtained at switching point. So there is a trade-off between dynamic range and SNR at signal switching point. The objective of this work is to develop a CIS with an over 120 dB dynamic range and over 32 dB SNR at all switching points. To achieve the objective, over 10 mega electrons fuel capacity is equivalent to maximum SNR of 70 dB are needed for high saturation signal. In this work, to improve saturation, trench capacitor is introduced as two-stage LOFIC. We designed and prototyped the chip and experimented the principle of two-stage LOFIC. These figures show block diagram of CIS with two-stage LOFIC. Two-stage LOFIC, LOFIC 1, and LOFIC 2 are integrated adjacent to the photodiode in each pixel. The chip has 3 pairs of analog outputs for high sensitivity signal S1 and high saturation signal S2 and S3. I'll explain the operation of two-stage LOFIC. First, I'll show you the operation of high sensitivity signal S1. Under low light illumination, photoelectrons are accumulated in a photodiode at T1. Then let out S1 reset level at T4. At T5, photoelectrons are transferred to the small capacitance FD, and at T6, S1 signal is read out by converting photoelectrons at FD. Second, I'll show you saturation signal S2. At T2, S2 reset level is read out. Under middle illumination, overflow photoelectrons are accumulated in LOFIC band at T3. And at T7, photoelectrons are transferred to the FD plus LOFIC band. And at T8, S2 signal is read out by converting photoelectrons at FD plus LOFIC band. Third, I'll show you high saturation signal S3. At T1, S3 reset level is read out. Under high illumination, overflow photoelectrons are accumulated in LOFIC2 at T3. At T9, photoelectrons are transferred to the FD plus LOFIC band plus LOFIC2. At T10, S3 signal is read out by converting photoelectrons at FD plus LOFIC band plus LOFIC2. These three signals are read out at every frame with the same readout timing. These figures show pixel layout, cross view of LOFIC to photodiode, and two-way TEM images. Rectangular shaped trench capacitors were integrated densely in parallel, as shown in pixel layout. One of them is LOFIC 1, and the others are LOFIC 2. Deep PWell was implanted to cover the entirety of LOFIC. The concentration of deep PWell were optimized in order to obtain the uniform capacitance in the signal range of LOFIC. Furthermore, PWell and deep PWell form a potential gradient so that the photoelectrons generated deep inside are drifted into the photodiode. This figure shows chip micrograph of the developed CIS. The number of effective pixels is 128 times 128, and the pixel pitch is 16 micrometers. I'll explain photoelectric conversion characteristics. We obtained good linearity of high sensitivity signal S1 and high saturation signal S2 and S3. 122 dB dynamic range with linear response was obtained under single exposure, and over 35 dB SNR at signal switching point, and the maximum SNR of 70 dB were achieved due to two-stage LOFIC. These figures show the sample images captured under single exposure. Sample images of a light bulb, a grayscale chart, printed paper, and two stuffed animals was captured. The stuffed animals on the left was illuminated with high-intensity lights from both its front and back to simulate the gray phenomena. The other stuffed animals on the upper right was placed in a dark box. The S1 signal captured the upper right stuffed animal under low light condition. The S2 signal captures the printed paper on the back and the grayscale chart under high light illumination. The S3 signal captures the light bulb filament and the stuffed animal on the left under very high light condition. The results show that the developed CIS exhibits a single exposure wide dynamic range performance. The left figure shows a wide dynamic range sample image, combining S1, S2, S3 with gamma correction. The center figure shows sample image combining S1, S2, S3 without gamma correction. The right figure shows sample image combining only S1 and S3 without gamma correction. You can see the image quality of the center image is much better than right one, especially inside of the red frame. I'll summarize performance of the developed CIS. We achieved over 120 dB dynamic range and over 32 dB SNR, and the maximum SNR of 70 dB were achieved due to two-stage LOFIC. This figure shows the relationship of dynamic range with other linear response CIS and SNR at switching point. Over 120 dB dynamic range and 35 decibel SNR at switching point are successfully achieved. This figure shows the calculated relationship between pixel size and capacitance density required for each dynamic range. Here, calculation was carried out with the conditions that the capacitance area ratio is 80% of the pixel area. The number of input referred noise is 1 electron, and the signal voltage range at floating diffusion is 0.8 volt. Several high capacitance density technologies have been reported and drawn as a band in the graph. By combining these capacitors with 3D stacking technologies, it's highly possible to achieve a dynamic range of over 120 dB even for a few microns pixel pitch using the proposed two-stage LOFIC architecture. I'll conclude my presentation. Two-stage LOFIC prototype image sensor chip was presented. 122 dB wide dynamic range with linear response, over 35 dB SNR at all switching points. Scalable with high density capacitor technologies were achieved in a single exposure with two-stage LOFIC. The developed CIS is highly adaptive to many applications with strong contrast of light illumination. Thank you for listening.
Thank you very much. So now we'll be going through any questions or any discussions or comments you would like to make. So if you want to turn your webcam on, and if there's anything you want to discuss, just unmute or put your hand up, and I'll come to you. Yes, Chris?
Sorry. So hi, it's Chris Dainty. I'm with Xperi now in Ireland. So this seems too good to be true. So what are the downsides? I mean, what's the penalty? Because as you know, this is a very big current issue in automotive, ADAS, automated driving, and it's a very big topic of discussion to have high dynamic range, which is essential. So there must be some downside. So what's the downside?
Okay. This is a schematic of LOFIC pixel, and in the LOFIC pixel, we extra components, one transistor and a capacitor has to be added to the inner pixel compared to the normal 4 transistor pixel. So we need more space than normal CIS. So it is a disadvantage of this approach, but in this graph, the high density capacitance have been developed recently. So with these capacitance and combine the 3D stacking technologies, this will be improved and pixel size shrinking is possible.
Okay, and yeah, so the pixel sizes used in automotive tend to be a bit larger, like 3 microns or 2 or 3 microns. Okay. And you presumably one would use lensless arrays as just as normal to help counteract this. Okay, thanks very much. Thank you.
Thank you.
Okay. I've got a similar question to this. It's a very my background isn't so much into the engineering side, but is there a limitation in the size of the sensor? Because you've got 128 by 128.
Yeah.
Is there a limitation to making this larger or higher resolution?
No, I think this technology can adapt you to larger pixel size sensors, and no need to special circuit or other technologies. Yeah.
Has anyone else got any comments or questions they would like to make? Go ahead. Sorry, is that Sankyuan?
Hi, this is Song Hyun. Thank you for the presentations. I have a question. The switching point. How do you decide? How do you decide the switching point, and then can you explain that more about the switching points?
Okay. This is a photoelectric conversion characteristics, and the switching point is determined by the saturation level of each signal. And for example, switching point at S1 and S2 is saturation point of S1, and the S2 and S3 switching point is same as S1 and S2, and this is determined by the S2 saturation level. And if we increase the dynamic range, the switching point is decreasing, and so at the beginning of the chip design, we get the SNR value at switching point and calculate the FD capacitance and LOFIC capacitance for making sufficient get sufficient SNR at switching points.
Okay. Okay.
Danny Rich, do you have a question?
Yes. So early on in the presentation, you said the gain was proportional to 1 over the capacitance, but then your curve showed that the highest gains were for the highest capacitance. That seems not intuitive to me.
Could you repeat the question?
Yes. So in one of the early slides, you showed the gain as being the charge over the capacitance. And then later on, you showed the performance curves in which as the capacitance increased, pixels got smaller, capacitance went up, so did the signal. So that, yeah, this one. So this basically shows that as the capacitance goes up, then you're going from 120 to 130 to 140.
Yes.
So I don't understand how with the capacitance increasing, you get better gain.
This graph shows in this calculation was carried out with this condition, and with a certain pixel size is determined and capacitance area ratio is determined. The capacitance density needed for the pixel with achieving this dynamic range. And this dynamic range is determined by the fuel capacity. So the pixel size is shrinking. If the pixel size is shrinking, we need more capacitance density to achieving same dynamic range.
Okay, okay. Can this technology be adapted to a linear scan format rather than a square format?
A linear array sensor. Do you mean?
Yeah, so like we would use in process management where we're watching things move underneath the scanner?
Yes, it's adaptive.
So it could be adapted to that so we could get 120 dB on a process monitoring system.
Yes.
Okay, great.
Thank you. Okay. I've got a question in the chat that asks if you can control the switching point, the level manually or in the program, or is it fixed?
It's fixed at the designing.
Okay.
Yeah, because it's defined by the capacitance of the FD and LOFIC1 and LOFIC2.
Okay. Is there any further questions? Just checking some hands. Sangyan, is your hand still up, or have you got another question? No, it's just gone down. Okay. Okay. Let's see. I've got some further questions. Have you tried this in more real-world conditions, or is it still just in the lab with your stuffed animals, or have you got any video?
Okay.
Of this in real-world applications?
This is a sample movie of absorption imaging. This is a 5 milligram per deciliter glucose diffusion. And this is the experimental setup, and 5 milligram per deciliter glucose aqueous solution dropped into the cell with serological saline solution. And this experiment is aimed for non-invasive blood glucose measurement. And a diffusion of 5 milligram per deciliter glucose was clearly visualized. And the other one, this one is another absorption imaging. And this one is ozonated water absorption imaging. And this is an experimental setup. In the semiconductor industry, ozonated water, which is a kind of functional water dissolving ozone into ultra pure water, is widely used because it has a high removing effect against contamination of wafers and glass substrate. On the other hand, since ozone has short duration of effect by self-decomposition, and also a large amount of ozone is harmful to human bodies, it is important to monitor ozone concentration. And with this sensor, clearly visualize the sub-ppm concentration ozonated water.
Okay, thank you. Just checking any other hands to go up. Okay. From I didn't see it in your slides, but from the paper I saw that your spectral sensitivity is very quite large. If you start limiting it to let's say near infrared IR, is there any drawbacks to this?
This figure shows the spectral quantum efficiency characteristics, and the beat occurs due to interference of interlayer insulating film on photodiode. It's nothing to do with photodiode performance. And we use the 20 micron thick P epitaxial layer. High sensitivity in the near infrared region was achieved. And a sensor with higher sensitivity to near infrared light using a low oxygen concentration P-type substrate has also been reported.
Okay, thank you. Any further questions or comments? Sangyan?
Yeah, I have one more question.
Sure.
Is there any the frame rate limitation due to the kind of extra timing in the pixel readout?
Oh, okay. This is an operation timing diagram of two-stage LOFITreC, and there are 3 transfer timing. So compared to normal CIS, it takes a little longer time to read out, but it can design and faster frame rate is available. And in this sensor, the maximum frame rate is over 600 FPS because the number of pixel is small, limited. So the frame rate is depends on the pixel size, the number of pixels.
Okay, thank you. Well, I've got one more question. It's more of a general question on the applications of such a method. Is there any kind of like computational limitations to this? Can you use this in consumer grade cameras in a smartphone, or is it more based more on more scientific and imaging science applications, where you got the computation behind it?
Okay. In scientific applications, the sensor is has a very advantage because the maximum SNR is very high, and the normal current CIS is of the maximum SNR is around 40 dB, and this sensor is 70 dB. So it's a big difference and can capture the slight difference of the light signal and the highlight illumination. And in consumer devices, the pixel size needs to shrink to submicron pitch. So to adapt this sensor to consumer devices, we need to pixel shrinking by combining 3D stacking and high capacitance density capacitors.
So it's more of a physical restriction rather than any computational restriction.
No, I think.
Okay. Do we have any further points anyone would like to make or
There
discussion?
are points in the chat, Oliver.
Oh yes, so there is. If you may be working in the industries, and so if I believe this is asking if you the manufacturer of this sensor, and if you're working within the industry to try to manufacture such a sensor.
The question is, do you have the plan to manufacture this sensor for?
I think the question is, are you working with any companies to develop this?
Yes.
Okay. And the second question is there a difference in color or image quality tuning compared to the traditional HDR sensors used in automotive or IoT segments?
No difference. Yeah.
Okay. Is there any other hands up? I'm just checking. Okay. If there's no further questions or comments, I'll bring this this session to an end, and I'd like to thank Yasuyuki again. And if you have any questions later, you can always email him directly.
Okay, thank you very much.
So